We've started and we are online now. So, hello guys, in this video we are going to be looking at the stereochemistry, and under this we are going to look at everything that was taught and also take questions and answer from previous exam papers. Now to begin, let's start with what stereochemistry is actually about. Now, stereochemistry is a branch of chemistry that studies the molecular structure or the 3D molecular structure of compound. This is a branch of chemistry that studies the 3D molecular structure of compound. Okay? So the branch of chemistry that studies the 3D molecular structure of compounds is called stereochemistry. As name implies, stereo means what? Let me pick it out. Stereochemistry. Stereo means what? 3D. Why chemistry is there? So the study of the chemistry that studies the 3D molecular structure of compound is called stereochemistry. Now, why is stereochemistry important in pharmacy? Now, it is important to understand the actions of drugs, or let's say the pharmacological importance of drugs. Are we getting it? On living or on biological system. It's good that we study the stereochemistry of these compounds that makes up these drugs, and also of cell tissues like carbohydrates, proteins, etc. that we take into our body. So that is that for stereochemistry, the study of the 3D structure of compounds. Now, the next thing is, what is isomerism, and give the different types of isomerism. Now, I believe that this is not something that is new to us. Isomerism, as the name implies, is a phenomenon. Isomerism is a phenomenon whereby compounds have the same molecular formula. Isomerism is a phenomenon whereby compounds have the same molecular formula, but what? Different structural arrangement. Are we getting it? But different structural arrangement. So that phenomenon is what is called isomerism, or we can say different arrangement. Different arrangement. So whenever compounds have the same molecular formula but different arrangement, we call that what? Isomerism. For instance, let's look at 2-butene or 2-butene. This is the structure. Or let's say 3-butene, 2-pentene rather. This is 1, 2, 3, 4, 5. This is the structure of pentene. Now, if I should put a double bond here, it becomes what? 2-pentene from 1 to... At position number 2, you have the double bond. So you can call this 2-pentene, or you can say that this is what? Pent 2 in, indicating that at position number 2, there is what? A double bond. Is that understood? Now, let's look at 3-pentene and identify the similarities and differences between these two compounds. If you look at 3-pentene, this structure, 3-pentene is supposed to be somewhere around here. Whichever way you draw it, it's going to give you from either side. If you count it from here, this is 1, 2. So let's use hexane to illustrate this. I think hexane will be much more better. This let me add here. So this becomes number 5, and this becomes 2-hexane. 2-hexane, and this is what? Hes 2 in. Then let's say this is 3-hexane. Let's add one here. 3-hexane. Now, if you see the structure of 3-hexane, this is how many? 1, carbon 1, this is carbon 2, this is carbon 3, this carbon 4, this carbon 5, and this carbon 6. Now, if you look at these two molecules very well, if you want to write their structure or their molecular formula, You agree with me that here it has 3 hydrogens. This carbon here has 3 hydrogens. So you say this is CH3. This carbon here has just 1 hydrogen. So you say this is CH, double bond. This carbon here has just 1 hydrogen, CH again. This one has 2 hydrogen, CH2. These are many now, 1, 2, 3, 4. This one has CH2 and this has CH3. Now this is the molecular formula of this compound. Now coming here also, this one is CH3, then this one is what? CH2. Then when you come here, you now have CH, double bond, CH. Then this number 5 is CH2, and finally this is CH3. If you count the amount of carbons here, there are how many? 1, 2, 3, 4, 5, 6. As the name implied, they are hexane. So you say this is C6H. How many hydrogen? 3 plus 1 is 4, plus 1 is 5, plus 2 is 7, plus this is 9, and plus this is what? 12. So you say C6H12 for Hes2N, which is 2 hexane. Now coming here also, you have 1, 2, 3, 4, 5, 6, which is C6H. This 3 plus 2 is 5, plus this is 6, plus this is 7, plus this is 9, plus this is 12. So you see that the 2 compounds, they have the same molecular formula of C6H12, but different arrangements of the atom. In this case, what differs is the position of the double bond. The double bond is at position number 2 here, and the double bond is at position number 3 here. So we call this what? Isomerism, a phenomenon whereby compounds have the same molecular formula but different arrangements of the atoms. Are we getting that? Now, isomerism is not restricted only to double bond. We can have, let's say, this CH3, CH2, CH, here is B arrow, here is CH3. These these 1, 2. This is 2-bromopentane. And then if I can still draw this again, you have CH2, B arrow, then CH2, this pentane, 1, 2, 3, 4, butane rather, 2-bromobutane. 2-bromobutane. Okay, now I can still draw this in such a way that it will be like this. CH2, the Br is at position number 1, then CH2, CH, B arrow, not B arrow here again, then CH2, and here CH3. If you look at this compound very well, it's also what? This bromo, we can now say this is 1-bromobutane, or let's say bromobutane. But if you look at it very well, 1, 2, 3, 4. How many carbons? C4. How many hydrogen? 2 plus 2, 4, plus this is 6, plus this is what? 9. C4, H9, then 1 B arrow. Same thing applicable to this one. This one is what? 1, 2, 3, 4. C4, H. How many hydrogen? This is 3, 5, 6, and what? 9. H9, and then B arrow. So you see, they have the same formula, but different arrangements of atom. This phenomenon is what is called isomerism. Now, isomerism, the types. Let's talk about the types of isomerism. Isomerisms are classified into 2 types. We have one, the constitutionals isomerism. We have what? Constitutional isomerism. And then the other one is what? Not geometric, stereo. We have stereoisomers. So these are the 2 basic types of isomers. 1, constitutional isomers, and 2, what? Stereoisomers. Now, the constitutional isomers just talks about the different arrangements of what? Atoms. Different arrangements of atoms. For instance, let's take this compound CH3OCH3. What compound is this? This is the arrow O arrow functional group, and this is what? An ether. Then if you also write this again, you have CH3, CH2OH. This is what? Alcohol. This is the alcohol functional group. Are you hearing it? If you take these 2 compounds now and then analyze them, you discover something. They have the same molecular formula, which is what? C2H, then 6, and what? O. Then also analyze this. This will be what? C2H, 3 plus 2 is 5, plus 1 is what? 6, and then what? 1 hydrogen. So these two compounds now, they are constitutional isomer. The only thing that differs is the arrangement of what? Atom, but not in 3D form. So constitutional isomers differs in only the arrangement of what? The atoms. For instance, if you have, let's say you have something like this. This is 1, 2, 3, 4, 5. This is pentane. And then you have 1, 2, 3, 4, and then 5. This is what? 2-methyl butane. 2-methyl butane. If you look at these two compounds, they are almost the same. If you want to count the number, this is pentane. Normal pentane is C5H12. Also, this one is C5H12. What is the differences between the two? The arrangement of the atom. So the arrangement, different arrangement of atoms gives rise to what? Constitutional isomers. Different arrangement of atoms gives rise to constitutional isomers. While stereoisomer is the arrangement of atom, or let's say stereoisomers are atoms or compounds. No, they are not atoms. Stereoisomers are compounds. Stereoisomer, they are compounds with same molecular formula, but different spatial or 3D arrangements. They have the same molecular formula but different spatial or 3D arrangement. That is what stereoisomers are all about. Are we getting it now? We are going to look at the different types as time progresses. Now let's look at the different types of stereoisomers. Now stereoisomers are classified into two. We have what is called the conformational isomers and the configurational isomers. Now the conformational isomers, they are compounds that differs about a rotation, or that differs due to a rotation about a single bond. So compounds that differs due to rotation about a single bond are called conformational isomer. Rotation about a single bond, they are called conformational isomers. So all compounds that differ due to rotation about a single bond are called what? Conformational isomers. Why configurational isomer? We are going to look at them in details. Under configuration, that is where you have cis and trans, we have geometric, we have arrow and S nomenclature, we have E and Z. Now if you look at these two compounds, we have one trans-cinnamic acid and the other one cis-cinnamic acid. What can you say, or what can you see in between these two compounds? Now you discover that in this compound, the way it is, this one here has one hydrogen here. Let me make it point out. This one here has what? One hydrogen here. And this one here has one hydrogen here. You see that about the double bond, one of the hydrogen is up and the other one is what? Down. So when one hydrogen is up and the other one is down, like they are not facing the same direction, you call it what? The transform. So this is an example of configurational isomer. Okay? Configurational. Which in this case is what? The cis and trans, geometric, but in this specific case, it is a transform. Now look at this one. If you want to write this one, the hydrogens, one is here and the other one is where? Here. You see the way the hydrogens are arranged, they are at one side. Hence, you call this one what? Cis. So this is the cis isomer. Now we are going to discuss all these in detail, just like a brief of what we are expected to know in this lecture. Now let's go to conformational isomer. I said conformation talks about the arrangement around a single bond, or it arises due to the rotation around a single bond, rotation about a single bond. Now they are arranged in different projections or in different ways. We have the ball and stick model. the ball and the stick model. Then we have the sawhorse. We have the ball and stick, and then we have the sawhorse, and then we have the wedge and broken line, and finally we have the Newman projection. So let us look at the ball and stick, how it is like. As the name implies, ball and stick is just like a ball and a stick. Like you put a ball inside, you put a stick inside a ball. Let's say these are the two balls. Then you put a stick through, which is like the bond. Then you now add all these other components, like this, like this. This one like this one comes like this, and finally like this. Now this is hydrogen, 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 and then this is also hydrogen, hydrogen, hydrogen. Now this model is what is called the ball and the stick model. Is that okay? The ball and the stick model. Now what is the difference between this one? Each of these balls you are seeing here is a carbon atom. Each of the balls you are seeing here is a carbon atom. So you can see that we have one carbon here and then another carbon here. Now this carbon is carrying how many hydrogen? CH3. This one also is a carbon carrying how many hydrogen? CH3. So in this molecule, you now see the structure of this molecule. CH3 is what is here, and this is what? Ethane. Are you getting it now? So this is what is called the ball and the stick model. The ball and the stick model. Okay. Now we have what is called the sawhorse projection. The sawhorse is more like the ball and stick too, but it's quite different. The sawhorse projection uses this mechanism. Let me make it easier. I just want to show us one, whether it is staggered or not staggered. When we talk about the other ones, you understand when we say something is staggered and when the other one is not staggered. Now you have something like this. Now this is the ball and the stick, the sawhorse projection, where each of these points you are seeing here represents a carbon atom. Each of these points you are seeing here represent a carbon atom. Then these are of course hydrogens. Are you getting it now? These are hydrogen. So if each of these points represent a carbon atom, it means here will be CH and what? 3. And then this other will also be what? CH3. So this is what is called the sawhorse projection. So if they say give the sawhorse projection for a compound, this is what you are expected to draw for that compound. Is that understood? Now we said the ball and stick. Each of the balls represents a carbon atom. So if they give you two balls, it means they are telling you that there are many carbon atoms there? 2. Are we getting it? And the hydrogens attached to it. Now it may not be a simple molecule like ethane that just have 2 balls. There are some molecules that you have to, in place of these hydrogens here, you put CH3. That one now is telling you that we don't have only 2 carbons, but more than 2 carbons present in it. Is that understood? So let's look at the next representation. This one is wedge and broken line representation. Wedge and the broken line representation. Now this one has something like this. Then you have something like this. Then you have the wedge like this, where each of these points also represent what? Hydrogen, a carbon rather. So you have another one in such a way that you have the broken lines coming here, hydrogen, and then you have the wedge. So this one is called the wedge and broken line representation. Each of these ones, they have a carbon atom in them, or each of these points. Normally they ought not to be carbon here, so that we wouldn't be introducing carbon where it ought not to be. So we have something like this. This is hydrogen, and so on and so forth. Now this one is telling us that it is in plane. This hydrogen here is telling us that it's pointing away from us. Are we getting, like something is pointing away from you? It's represented with this dotted line. We tend to understand it when we are talking about the arrow and S configuration in future time. So this one now is still the same thing. Each of these points represent carbon. So we have carbon, hydrogen, and what? Hydrogen, which is CH3, CH3. 3. So let us talk about the other one, which is called the Newman projection. Now the Newman projection. Now the Newman projection is almost like the ball and stick, but it's just that it's telling you that two balls are superimposed on top of the other. Two balls are superimposed on top of the other. So for the Newman projection, you have something like this, where each of these ones now, they are what? Hydrogen. Now, there are two ways to draw the Newman projection. We have what is called the eclipse. This is where I want you to really pay attention to the eclipse. And what? Staggered. The Newman projection, there are two ways to draw them. We have the eclipse and the what? Staggered. So in this case, you have hydrogen also. Hydrogen and then another hydrogen. Look at the way I drew it. I drew some of the lines inside the main cycle, while the other is starting from the what? The cycle itself. Now, what does this tell us? It tells us that we have two cycles on top of each other. One of them is actually covering the other. That is why some of the lines started, like this one is the one on top. You can see all the lines. Are you getting it? Why the other one is what? Under. Because this other one is covering it. You cannot see where they meet. Is understood? So in this case now, you call it the this one is the staggered projection. Staggered. Why is it called staggered? Because all the hydrogens are as far apart as possible from each other. So you call this the staggered projection. Now the next one is the eclipse. It's still the same thing you are going to draw. Now, how do we show the ones that are outside? You say you draw it from inside the circle. So you have hydrogen, hydrogen, and hydrogen. Now the ones at the back, you represent them like this. This one is telling you that it is at the back, that this other circle is covering it. So automatically what this thing is telling us that we have two circles on top of each other, but you can only see one because one is covering the other. Is that understood? So now this configuration like this is also staggered. If we want to make it eclipse, how do we make it eclipse? Eclipse is when something is very close to something. So this one is close to this one is close to this, and this is close to this. What do you call this? Eclipse configuration. Is that understood? So this is staggered and this is eclipse. And in most cases, as time progresses, you tend to understand that the eclipse projection is less stable than the staggered. So it means that the staggered is more stable than the what? Eclipse. Is that understood? So let us continue with the lecture. Now, let's talk about torsional strain and torsional energy. Let's talk about torsional strain and torsional energy and then explain from there. Now, when we talk about torsional strain and torsional energy, now torsional energy is the energy that is required to rotate around a single bond. That means the energy that is required to rotate around this carbon to carbon bond is what is called torsional energy rather. Why torsional strain is the strain observed when a conformer, move from its ideal bond angle, ideal bond angle to another. Move from its ideal bond angle to another. You call that what? Torsional strain. The strain that is produced. Now let us assume that something is supposed to be angle. Normally, the sp3 carbons, according to what we know before, sp3 carbons, they are usually what? Their angle is what? 109.5 degree. Is that also? Now, if a particular compound now move from this 109 to let's say 60 degree, it means that that compound is what? Having torsional strain. Are you getting it now? It's having torsional strain. Now let's look at the Newman projection for propane. And then see the one that you think will be, we have higher torsional strain and so on and so forth. Now the Newman projection for propane is, you have something like this. One of these, you have something like this. Then you have this and this and this. Now we said if you add hydrogen here, it means what? Ethane. If you add hydrogen, then let's say this one comes here like this, another hydrogen and hydrogen, and then hydrogen. What did we say? We say in this thing it means that there are 2 circles, and 2 circles means what? 2 carbons, and each of the 2 carbons are superimposed on top of each other, right? So we have C2H, which is 1 2 3 4 5 6. C2H6 is what? Ethane. Now if we represent one of these hydrogen by CH3, what does it mean now? It means that one hydrogen will no longer be here, right? It means that here will now be how many hydrogen? 5. Plus the CH3 that we added now will now be how many? C plus C is C2 is what? C3. Then what? D plus this is what? H8. What structure is this? Propane. Are you hearing it now? So what we mean by this is that if we remove one hydrogen and substitute a CH3 group, it means we are increasing the length that can be formed. So in this case now you have C3H8, abi? Now how about if I remove one other hydrogen from here and then put CH3? What does it mean? It means we remove one hydrogen from here, right? Now if we remove hydrogen from here, what will be here? C7. Then plus CH3. Total now will be how many? C3 plus C3 is what? C4. Then H what? 10. What structure is this? Is it not butane? Are you hearing it now? So if we want to draw for that of propane has how many carbons? 3. So it means that we put 1 carbon here, which is CH3, and then here will be this. Now this structure of propane is what is called the staggered structure, or depending on how you want to call it, you call this one the staggered structure of propane. It can be represented in different way. So this is the staggered structure of propane, which we can also draw as, to be more precise, put the CH3 here. It become what? Staggered structure of what? Propane. Is that understood? Now, how do we now draw the eclipse? We said eclipse is when it is what? Close together. Staggered is when they are what? Stretched apart. Is that understood? So we now come here now. The staggered or the eclipse structure will be something like this. Then we have what? CH3. Is that understood? If we had CH3 there, the CH3 can be on top of any one of them. Can be the one outside, can be the one on top. Are we getting it? Then what are we going to have here? Hydrogen. This one now will be very close. We can have hydrogen here. Here is what? Hydrogen and what? Hydrogen. So in this case, what is this one telling us now? That they are what? Packed close together. So this is called the eclipse conformation of what? Propane. Why this is called the what? Staggered conformation of what? Propane. Staggered conformation of propane and eclipse. Now, what can we establish from here? Do you think that this one will have a higher energy than this, or this? Let's talk about the torsional strain now. Let's not talk about the energy. The torsional strain. Which of them do you think will have a more torsional strain? Is it the eclipse form or the staggered form? Which of them do you think? Which of them do you think will have the higher torsional strain? If you see these two structures, this one, they are far apart. Are you hearing it? Hence, they are stable. Why this one? They are what? Very close. Hence, there is what? Repulsion. You know, each of these one have electrons. There is repulsion. And because there is repulsion, what will happen? This one will be unstable. And when something is unstable, it means it has a higher what? Energy. Are you hearing it? So this one has higher energy as compared to this. Higher energy and higher what? Torsional strain. Are you hearing it? Because the molecules are what? Close together. Are you hearing it? Hence, it will be very, very hard for them to separate out, or let's say it will be because of their closeness, there is high repulsive forces between their electrons. Hence, the instability of the atom. Now, let's talk about the one for butane. Let's talk about the one for butane. Now, butane can go as far as eclipse, anti, gauge, and another eclipse. Now, let us draw the eclipse structure of butane. Something like this. Now, butane has how many carbons? That's 2 CH3 carbons. Now, if butane has 2 CH3 carbons attached there, when I mean 2 CH3, I mean aside from the cycles, we know the cycles are 2. Butane is C4H10. It means it has how many carbons? 4 carbons. We already know that this one here represents 2, 1 superimposed on top of the other. Now, this CH3, when the 2 CH3 groups that are represented are close to each other, you call it the eclipse form. Because we said that one circle is on top of this one is 2 carbons already, then plus this 2, making it to be how many? 4. So when the 2 CH3 groups are close, you call it the what? Eclipse configuration. Of course, we know these are all hydrogens. Now, how about if you come here and draw anti? Anti means one is on top like this, and the other one is at the bottom like this, in such a way that they are very far apart from each other. This hydrogen are what? Hydrogen. This anti-configuration. So that kind of configuration whereby the 2 CH3 groups are far apart, you call it the anti-configuration. Now, this configuration can also be in such a way that you have it like this. CH3, then this other CH3 group is here, and this hydrogen is here, and then you have H, and H. Now, the 2 CH3 are close, but they are not eclipsed to each other. One is like, let's say if you want to use orthogonal, is at the ortho position. Are you getting it? These ones, they are close together, you call them eclipse, but this one, they are spread apart, but this one is closer to this. Are you getting it now? You call this one what? Gauge staggered. You call this what? Gauge staggered. Now, there is another way that this can also be drawn in such a way that you have CH3 group, then you have what? This hydrogen here, then of course this one will come here, and then this hydrogen, this hydrogen, this hydrogen. What do we call this? This is what? Another eclipse. But this eclipse is between hydrogen and what? One of the CH3 groups. Why this one is also a CH3 group? So this is between one hydrogen and one CH3 group. This is between one hydrogen and what? One CH3. Why this eclipse here is between 2 CH3 groups? Are you getting it now? So the eclipse can be in two forms. It can be in the form of one hydrogen and one CH3, the 2 CH3 groups, and the staggered can be in two forms. We can have the anti and the what? Gauge. The anti is the one that they are just like opposite each other, CH3, CH3. Why the gauge is when they are very close to what? Each other. Is that understood? So that is for that. Now let's talk about the conformation of cyclopropane, rather. Conformation of cyclopropane. And then from here, we'll be able to predict. Now, before I go, in this configuration, the staggered is more what? Stable compared to the what? Gauge staggered. This staggered one, which is the anti-staggered, is more what? Stable compared to this gauge staggered. Then before you talk about the two eclipse. Now, among the two eclipse, you agree with me that this one will be more stable than what? This, because this one, the two bulky group are close together. Are you getting it now? So that is that. The anti is more stable. In some cases, you may just be given the structure: eclipse, anti, gauge, and another eclipse. Which of them do you think will be more stable? Correct answer is what? Anti is more stable than the other. Now, let's talk about for cyclocompounds. All the compounds we'll be talking about since are what? Straight chain. And of significant importance we talk about is what? Ethane, propane, and what? Butane. Those are the ones that can be represented with this staggered and gauge staggered. I will get a clear explanation of what he's talking about. And these representations I just gave here are called the Newman what? Projection. Now, from the Newman projection, you'll be able to know the one that is staggered and the one that is what? Gauge staggered. If they give you the Newman projection, you should be able to draw the one that is staggered and the one that is what? Gauge staggered. Now, let's talk about conformational isomerism in cyclopropane. Now, before we talk about that, let's talk about let's go back to our primary 2 mathematics. Now, in mathematics, we are told that the sum or the angle of a polygon, is given as 18 bracket n minus 2 all over what? N. It's given by what? 18 bracket n minus 2 bracket what? N. Are we getting it now? So, if we are talking about cyclopropane has what? How many angles here? 3. Are you getting it now? 1, 2, 3. So it means n is equals to what? 3. Is that not so? So if you substitute this in, what will it become? 180 bracket 3 minus 2 all over what? 3. And this becomes 3 minus 2 is what? 1. In 180 times 1 is what? 180 divided by 3. And 180 divided by 3 will give us what? 60. Now, so it means that each angle of the cyclopropane is what? 60 degree. Are you getting it now? Now, when we talk about torsional strain and the rest, we said is the deviation from the agreed angle or from the exact angle. Now, normally, all alkanes, according to what we know, all alkanes are, what kind of hybridization do they undergo? All alkanes are what? They are sp3 hybridized. Is that not so? All alkanes are what? sp3 hybridized. How about alkenes? Alkenes are what? sp2 hybridized. Is that understood? sp2 hybridized. And then alkyne are what? sp hybridized. Now, everyone knows this. Now, another thing that you must take into cognizance is what is the angle of sp3 hybridization? Is normal tetrahedral structure of what? 109.5 degrees. Is that not so? Now, we already calculated that for cyclopropane, it has this shape. This is the shape of cyclopropane, which is a triangle. Everyone knows that. Where each of these are what? Carbon, carbon, carbon. Now, we calculated that each of the angles here will be what? 60 degree. Now, what should be the normal angle between 109.5 and 60 degree? What should be the normal angle? The normal angle is 109.5, rather, which is the angle for sp3 hybridized carbon. And why are we using 109.5 and sp3 hybridized? Because cycloalkane is what? An alkane. And all alkanes are what? sp3 hybridized. And they have a bond angle of 109.5 degree. Is that understood? Now, but the bond angle of this is what? 60 degree. It means that it moved all the way from 109.5 to what? 60. So there is a very high torsional what? Strain. Are you getting it? There's a very high what? Torsional strain and torsional energy. And hence, cyclopropane ring is what? Most not stable as compared to others. Are we getting it now? So that is that. Sorry. So the ideal words to use to call this, let's not use torsional strain, let's use angular strain. There's a deviation from the normal angle, like it's supposed to be 109 for all of them to be packed together, for all of them to be stable, but because it's now 60 degree, there is what? Like a compression from normal 109 is greater than what? 60. Are you getting it? So the angles are packed together, hence is what? Unstable. Now let's look at cyclobutane. What is the structure of cyclobutane? This is how it is, right? Now what would be each of the angle? From here we already see that is what? 90 degree. But let us calculate this. From the formula I gave is what? 180 bracket what? N minus 2 all over what? N. Now the reason why you ought to just know this formula is because when you get to the exam hall, sometimes they may say explain the conformational isomerism of cyclobutane in relation to their angular strain and which is more stable and which is not what? Stable. as compared to each other. Now let's look at cyclobutane. How many angles does it have? How many carbons does it have here? 1, 2, 3, 4. It means that in this compound our N is equals to what? 4. Now if N is equals to 4, what would this be? This will now be what? 180 bracket 4 minus 2 divided by what? 4. Now this becomes 180. Let's say this will now be, let me put it up here, 180 times 4 minus 2 is what? 2 divided by 4. Is that also? 2 going to here 1, 2 going to here 2, 2 going to 180 is what? 90 degree. So it means that each of these angles here are what? 90 degree. Is that also? Now compare 90 degree to 109.5. Of course you see that there is also what? Angular strain here. Are you getting it? But not as compared to that of what? Cyclopropane. Cyclopropane bond angle is around between 60 and 109. There is a wide range of difference between them. So this one is what? 90 and what? 109. So can we say that cyclobutane is more stable than cyclopropane? Yes. Are we getting it? Because it has lesser angular strain as compared to what? Cyclopropane. Is that understood? Now let's talk about that of cyclopentene. Now cyclopentene is what? This is structure. What will be the bond angles for each of them? Now in this structure our N is equals to what? 5. So it becomes what? 180 bracket N minus 2 divided by what? N. Now this formula is something that you should know, so that you don't go to the exam and start thinking of what is the bond angle for this, what is the bond angle for this. You just put it. This becomes 180 bracket N is 5. 5 minus 2 divided by 5. And this will become 180 times 3 divided by 5. I think this will give us 540 divided by 5. 540 divided by 5 is what? 108 degree. Now what is the bond angle? 108 degree. Is that understood? 108 degree. Now if the bond angle is 108 degree, what is the normal bond angle for alkanes? 109.5 degree. Now you see that the difference is not that much. So there may not really be angular strain here. Are you getting it? Because why? The two angles, the one that is expected and the one that is what? Actually form is almost close. Are you getting it? So there will be no angular strain present here. Now let's talk about the last one, cyclohexane. Cyclohexane structure is something like this. Now cyclohexane, it has N is equals to what? 6, which is what? 108 plus bracket N minus 2 all over what? N. 108 bracket 6 minus 2 all over what? 6. And this becomes 108 bracket 4 all over what? 6. And this gives us what? This here 1, this here is what? 2. Are you 3 rather. Then 180, this 2. Now 180 times 2 is what? 360 divided by 3 is what? 360 divided by 3 is what? 120 degree. Now you also agree with me that this one normally is 109.5 degree and this one is what? 120. So there will be what? Angular strain. But cyclohexane, it has a way of actually arranging itself in two forms, most especially the both and the what? Shear form. The shear form is more stable than the what? Both form. Now when it arranges itself in the both form, it arranges it in such a way that the bond angles now will now be assuming that of 109.5. And most of the molecules that we talk about in chemistry, pharmaceutical chemistries and every other thing, they are usually what? Cyclohexane. For instance, glucose it has a cyclohexane ring. Are you getting it? Most of all these molecules, they have cyclohexane ring. So let's come back now and talk about the two forms, the shear and the both. Now if I want to draw them, the both form, let me draw the shear form first if I can still remember how to draw it. Something like this. Then you have another one coming here. Now it looks like this. This is the shear form Please don't laugh at my diagram. Now, as it is like this, you are laughing. I think it makes more sense like this. Now, there are two types of hydrogens here. We have one, the axial, and another is what? Equatorial. Now, the ones that are pointing up are called the what? Axial. And the ones pointing this way are called the what? Equatorial. Is that understood? So you should take note of this. Equatorial and axial. Same thing applicable here. You have equatorial, then let's say this one's continues like that. We have the equatorial. All these ones, they are axial rather. Then this one is what? Equatorial. This axial. Then this last one, you have the axial. And this one is what? Equatorial. And then finally, axial, whichever way you want to call it, like this. This is how it is. Are you getting it? This is the shear form. The shear form is more stable than the boat form. The boat form is something like this. This is how the boat form is. You have all the hydrogens also, axial, equatorial, and that. So if you are asked, draw the boat and the shear form of cyclohexane, you should be able to draw them. And the one that is more stable, which is more stable, and then label the equatorial and axial hydrogen. You should be able to do that. Okay, all these ones, you know, there's hydrogen here, of course hydrogens here, and then what? Finally hydrogens here. So that is that for the cyclohexane. One is more stable than the other. The shear form is of course more stable than the boat form. We have the half boat, but I'm not going to draw that. Now, if you look at this structure very well, normally we are supposed to have 12 equatorial and 12 axial. Let's count. I mean, we are supposed to have 12 hydrogens in total. Out of the 12, 6 are equatorial and 6 are axial. Let's count. This is 1, 2, 3, 4, 5. Okay, this is 1, 2, 3, 4, 5, 6. All these ones are what? Axial, facing up and down. No, I counted equatorial. This is 1, 2, 3. Then this is 4. And then one of these one is supposed to be here also. 4, 5, then 6. Just forget about the counting for now. Let's not waste our time trying to spot out equatorial and axial. Are we getting it? Now, there's another thing that I want us to really pay attention to, and that is all the substituents present here are what? Hydrogens. All the substituents present here are what? Hydrogen. How about in a case where there is, let's say, a group that is more bulky than hydrogen? Let's say CH3. Now, in that case, there will be steric hindrance. And there will be what? Strain, torsional strain. Are you getting it? There will be torsional strain. And in most cases, if the bulky group is at the axial position, there will be more strain than when it is in the what? Equatorial. So it is better that a bulky group that is coming actually occupy the what? The equatorial than what? The axial. Reason being that if it is at the equatorial plate, it will be what? It will cause what? Strain. Steric hindrance. Is that understood? So if they say which of them will be more stable, let's say they put a substituent here and they put another substituent, or let's say they gave you two structure. One, the substituent is here, and then let's assume this is also shear. Assumption now. Let's assume this is also shear. This is shear. Now they put one of the substituent here, and then they put another one here. And they ask which of them will be more stable. What would you say and why? The answer is which of them will be more stable? Equatorial. Why? Because of what? Steric hindrance. Are we getting it? It undergoes more steric hindrance when it is at the axial as compared to what? The equatorial. Is that understood? So that is that. Now let's talk about chiral carbon center. I believe this is like 199th time of talking about chiral carbon center. We said chiral carbon center is also called asymmetrical. It's also called what? Asymmetrical or what? Stereogenic carbon center. Now, and it is a carbon center that has how many groups around it? 4 different groups. So if we have C, let's say S, Y, Z, and W, all the groups here are what? Different. So this carbon center is called what? Chiral. Now, how about if we have something like this? X, Y, X, W. Is this chiral? No. Why? Because the groups around here are what? The same. These two groups are what? The same. So this is not a chiral carbon center. Now, let's look at enantiomer again. Now, we say enantiomers are what? Stereoisomers. Enantiomers are what? Stereoisomers that are non-superimposable. Stereo what? Isomers that are what? That are non-superimposable mirror images. That are non-superimposable mirror images of what? Each other. Mirror images of each other. Those are called enantiomers. Are we getting it? And in organic chemistry, or let's say in what we are talking about now is stereochemistry. Now, the number of stereoisomers that can be formed is given by 2 raised to the power of what? N. The number of stereoisomers that can be formed is given by 2 raised to the power of what? N. Where N is the number of what? Chiral carbon center. N is the number of what? Chiral carbon center. So if a compound has 2 chiral carbon center, it means it will form how many stereoisomers? 4. If it has 3 chiral carbon center, it means it will have how many? 8. Not 6. 8. If it has 4, it will be how many? 16. Is that understood? So that is that. Now, enantiomers are stereoisomers that are non-superimposable mirror images of what? Each other. And how do you determine them? They are classified into how many forms? 2 forms. Are we getting it? The D and the what? L. This is not new to us. We say if the OH group at the penultimate, which is second to last carbon, the penultimate, which is second to last carbon, is at the right hand side, what do you call it? You call it the D isomer. Why, if it is at the left hand side, what do you call it? The L what? Isomer. Are we getting that? Now, we are going to designate the different enantiomer, but before then, let's talk about the properties of enantiomers. Now, enantiomers share same physical and chemical properties, but their interaction with plane polarized light differs. The only difference between 2 enantiomers is the interaction with what? Plane polarized light. Are we getting it? Differs. This gives rise to what? Optical isomers. Are you getting it now? So when enantiomers are placed in a solution, what happens? They either rotate light to the left or to the what? Right. Now, if they rotate to the right, we call it dextrorotatory. Now, if they rotate to the dextrorotatory. Now, if they rotate to the left, what do you call it? Levorotatory. Are you getting it now? Levorotatory. So those are the. If it rotates to the left, we call it what? Levorotatory. So that is the only thing that distinguishes between enantiomers. They share same physical property and chemical property, but their interaction with plane polarized light does what? Differs. Are you getting it now? So it may be asked, enantiomers have same physical and chemical property. So if it's to the right hand side, you call it dextrorotatory. If it's to the right hand side, you call it dextrorotatory. Why? If it is to the left hand side, you call it levorotatory. Now, how to designate the configuration of enantiomer? We have D-glyceraldehyde and L-glyceraldehyde. What will be their structure? Now, D-glyceraldehyde is this. This is the simplest monosaccharide of biological importance. We have the CH, then what? OH, and then, this gives us what? H, and this gives us what? CH2OH. OH. Now you see in this case now the OH group is at the right hand side, so you call it D-glyceraldehyde. How about this? COH and then C. Here is A, O, and what? OH, and here is what? CH2OH. Where is the H? The OH rather. The OH is at the what? Left hand side. So you call it what? L-glyceraldehyde. Now, which of the carbon did we use? Penultimate. When we say penultimate, we mean second to last from the group here. Second to last. Second to last. So this carbon 1, this 2. This 2 and what? 3. This second to last. The last is what? 3. Second to last is this. So if the second to last carbon is at the right hand side, you call it what? The isomer. Why if it is at the left hand side, you call it what? L-isomer. Now let's look at this other one. Dihydroxypropanoic acid. Propionic acid. Now this one is, okay, let's look at the structure of 2,3-dihydroxypropanoic acid. Now let's look at this together. The acid is double bond O, and here become what? OH. Are we getting it? Then here is what? COH, H, and here is what? CH2OH. That is what you have here. 2,3-dihydroxypropanoic acid. Are you getting it? Dihydroxy, 2 hydroxy group. At position number what? 2 and 3. Are you getting it now? Now, why is it the D form? Because of the OH group at the right hand side. Are you getting it now? Now, let us draw for the other one. This is L. So, what do you expect for L? Propionic acid. What do you expect for L? This C. Now, for L, the OH will be at this side. Then we now have what? H. And here will be what? CH2OH. Is that understood? So, this one at the OH is at this right hand side. So that is the difference between the D and the L form. So if you are given any compound, they say indicates D and L form, you should be able to do that. Now let's look at the next one. The next one is arrow and S configuration. Arrow and S configuration. Now the arrow and S configuration was actually initiated by a man called Can Ingold Prelog. The Can Ingold Prelog arrow and S system. They are different people. Are we getting it? Christopher, then one other name like that. Okay, now what is the major postulate of the Can Ingold Prelog theory? Now, Can Ingold Prelog says that what you do in this case is assign priority to each of them assign priority to each of them around the chiral carbon center. Now, if you assign priority to each of them here, what do you think will be the order of priority? Now, the order of priorities is in accordance with atomic number. It's in accordance with what? Atomic number. So the one that has the highest atomic number have the highest priority. The one with the highest atomic number has the highest priority. And then if that atomic number, if that particular particular atom rather, cannot define the one that has the highest priority, what do? You go to the next. Now, before I talk more, you see that C, if you have a double bond like C double bond O, this one is assumed as C bonded to oxygen, then oxygen bonded to what? Another carbon. This is how you see something like this. Are you getting it? C bonded to oxygen, then another carbon. So you see them as two different atoms entirely, like carbon to oxygen, another what? Carbon to oxygen. You don't see it as one carbon to one oxygen. Is that understood? So your priority, you break them down. You can say this is carbon, this is what? Oxygen, and what? Oxygen, like this. Is that okay? So that is that for the Can Ingold Prelog principle. Now, another thing that you also need to know about the Can Ingold Prelog principle is the configuration or the wedge structure. Now, in most cases, the lower priority group is usually the one on the wedge structure, which is this structure here, and the highest priority group is most time the one on this other structure here. So we are going to stop here for this session. Please make sure that you subscribe to this channel, turn on the notification button so that we notify you whenever we post a new video. And then after now, I'm going to bring in the part 2 to continue with the arrow and S system of nomenclature. Thank you.